In today's video, we're going to be going over how this device works. This is an emergency flashlight that has two ways to provide the energy for the battery. The first way is the solar panel, and the second way is this hand crank. Now, in today's video, we're going to focus on how the solar panel generates the energy, and we're going to be looking at how the LEDs work. Without further ado, let's open it up. This is the inside of the flashlight. The first thing you'll probably notice is the majority of the flashlight is filled with these gears. What these gears allow us to do is when we turn the hand crank on the outside of the device, it will spin these gears, which will in turn spin the generator located right here, this metal piece. Now, what's interesting about a generator is a generator and a motor are fundamentally the same thing, just operating in the opposite direction. Here, the generator is taking the mechanical energy of you spinning the crank and turning it into electrical energy, which will be stored in the batteries located in the back. If you were to hook up this generator backwards with the battery connections, you could actually get it to spin the hand crank in the front, turning the electrical energy into mechanical energy, as motors do, in particular electric motors do. Now, other than that, you can see we have a lot of wires, two of which are coming from the top. These are the two coming from the solar panel on the outside, so you can't see too much on the inside from that. And all of these are connected through this chip to go back to the battery. When this switch on the side here is flipped, it will turn on the LEDs in the front. The first thing we're going to focus on is how this solar panel provides that electrical energy for the batteries. Let's take a closer look now.
Diodes. Diodes are so important to us in the world in which we live. They are found in items we encounter throughout each day, including light-emitting diodes, or LEDs, transistors, and basically every electronic device we use, from computers to phones to solar cells. So what is a PN junction diode? If they are this important, shouldn't we understand something about how they work? What defines a diode? A common definition is a semiconductor device with two terminals, typically allowing the flow of current in one direction only. Let's consider this fence with a cement mixer as a diode. The reindeer approached the open fence from within, setting off a motion detector. This sets the rock-filled cement mixer rotating, making quite a racket. In addition, the black hood begins moving. The commotion scares the reindeer back into the safety of their pen. Alternately, a stray reindeer approaches from the outside and is able to walk through the gate unhindered. PN junctions work in a similar one-way mechanism. Let's take a look inside. This tetrahedral structure represents the diamond lattice structure of a silicon semiconductor. Silicon has 4 valence electrons, which are bound within this lattice. Think about what would happen if we replaced a few silicon atoms with an alternate but like atom. Consider where boron and phosphorus lie relative to silicon in the periodic table. Silicon has 4 outer valence electrons, which are bound in the lattice. Boron has 3 valence electrons. Thus, boron could displace the silicon in the lattice, but would leave an electron hole for the missing electron. Phosphorus, on the other hand, has 5 outer valence electrons. Thus, a phosphorus doping would add an electron for each phosphorus atom. These holes or electrons are then free to move within the lattice. Adding a trivalent atom, such as boron, leaves an empty electron hole. We will talk about the hole being free to move, yet that is not really the case. It is the electrons from a neighboring atom transitioning to fill the hole. Nevertheless, we will speak of this process as a hole moving. Adding phosphorus adds a free electron. That is an electron that is relatively free to move about the lattice. Silicon itself possesses limited conductive properties. Doping is defined as the process of adding impurities into a semiconductor to improve the conductivity. Doping silicon with boron and phosphorus leaves an abundance of freely moving holes on the P section of the diode, and an abundance of freely moving negatively charged particles on the N section of the diode. When brought together, the P and the N sections form the diode. Depending on the applied voltage, these holes and free electrons can can overcome the central barrier and transition from one side to the other. This barrier section is called the depletion region. When we add a voltage, we add a forward-moving potential difference. That is a negative cathode on the N-type junction and a positive anode on the P-type junction. The barrier between the junctions is reduced. Migration of free particles is then favored, leading to a lower energy state. The energy barrier is low enough that this transition can occur and current flows. This state of the PN junction is called forward bias. Given a voltage supply, both holes and electrons cross the junction simultaneously. The height of the barrier potential at the junction is lowered by the forward biasing voltage and allows current flow.
Now that we have a better idea of how PN junctions work, we can look at them in the context of the solar panel. Solar panels create current by electron-hole pair generation. The photon strikes the doped semiconductor depletion zone and generates an electron-hole pair. You can see this in the animation below. Now let's see what this looks like in the flashlight. Solar panels are just another example of PN junctions, but they differ slightly from the one that we are currently familiar with. Solar panels are PN junctions that operate in reverse bias, meaning their depletion zones will be larger. When an incoming photon from the sun strikes a depletion zone, it generates an electron-hole pair. The electric field in the depletion zone creates a steady flow of electrons, while the battery is charging. The electrons flow in the opposite direction of the net electric field, while the holes flow in the direction of the net electric field. When the electrons charge the battery, they enter on the negative side, and a new electron escapes from the positive terminal. The net electric field drives electrons through the battery, reversing the chemical reactions in the battery and storing potential energy. Here's an animation of the full process.
Now that we've seen the solar panel work, we're going to switch gears to the LEDs. Now, what's interesting about LEDs is just like the generator in the back acting as a motor in reverse, the LEDs act as a solar panel in reverse. Let's see how that works now.
While solar panels typically work by generating electron-hole pairs inside of the depletion zone of a PN junction, LEDs work in the opposite way, where electrons recombine with holes in pairs inside of the depletion zone. When recombination occurs, an electron falls into a hole, and the excess energy is emitted as a photon of light with a characteristic wavelength. The wavelength of this light will depend on the energy levels of the LED that you're using. Now let's look at this in the context of the flashlight. Remember, LEDs are just another example of a type of PN junction. The way they differ from the solar cells is that LEDs typically operate in forward bias, where the depletion zone is much smaller and the electron holes can recombine inside of the depletion zone. As the electron falls into the hole, the excess energy is then emitted in the form of a photon with a characteristic wavelength. Here's the full animation again.
I hope you enjoyed your closer look at this flashlight. It has a lot of pretty cool technology in such a small package. Have a good rest of your day.